three operators in logic known as conjunction, disjunction, and negation. We'll start with the definition of a statement, also known as a proposition. It's a sentence which is either true or false. Now we're going to take a look at a few examples, one of which is not a statement. There's 4 examples. Which one do you think is not a statement? In other words, we can't just say this is true or false. And the answer is number 3. Not a statement because we don't know if it's true or false. Depends on what X is. The other 3 are statements. Now typically P, Q, and R are the letters we use to represent statements. Any variable could be used. Conjunction, disjunction, and negation are operators or connectives that are going to create new statements from component statements. Here's the symbol for AND, P and Q, which is the conjunction of P and Q. Here's the symbol for OR, P or Q, and that's known as the disjunction of P and Q. Here's the symbol for NOT. That's not P would be written with that tilde, then the P, and that's the negation of P. Some people find it useful to think of this AND looking sort of like an A, just to help remember which one is AND. Now there's one other symbol for NOT which you may run into, and it looks like this. So these 2 symbols are both used for negation or for NOT. P and Q is a compound statement. We can decide if it's true or false depending on the truth values of its component statements. That would be the P and the Q. Let's consider these possibilities. If P is a true statement and Q is a true statement, well, then clearly P and Q would also be a true statement. Now suppose either one of P or Q are false. Can our P and Q statement still be true? Let's look at an example for this. Let's say our compound statement is Sam is a boy who plays piano. Now if Sam is not a boy, I think we could say the statement is false. If Sam does not play piano, I think we could say the statement is false. Symbolically, one statement, let's say P stands for Sam is a boy, Q is Sam plays piano, and then we have our compound statement P and Q. So if one of the components is false, in other words, if P is false, then P and Q is false, and similarly if Q is false, P and Q is false. And surely if both P is false and Q is false, then P and Q will be false. We're ready to define this conjunction. That's the AND. So here we go. Let P and Q be statements. The conjunction of P and Q, denoted in this way, is true only if both P and Q are true, and it is false otherwise. And that's P and Q. Here's the symbol, and here's how you might read it. We can also use a truth table to define P and Q. And here's what a truth table looks like. We're going to put in P as one column, Q as another column. We're going to do P and Q as a third column. I'm doing it kind of sloppy. I'll show you a nice neat one in a moment. Now we could have P is true and Q is true. That's one case. Another case is that P is true and Q is false. So that's all the cases where P is true. But P could be false and Q could be true, or P could be false and Q could be false. I think if you look at that and think about that, you'll see those are all the cases. For our P and Q truth value, remember, it's only true if they're both true. That's only one case. In all the other cases, at least one of them is false. P and Q is going to be false. So that's how we set up a truth table, and that really defines the truth values for P and Q. So here it is all nice and neat. I told you I'd give it to you neatly. So again, true only if they're both true, false in every other case. Let's talk a little bit about the setup of this truth table. Notice that we list all the combinations, and the last column, this column here, is alternating true, false, true, false. So that's a little bit of a system of how we got every combination of P being true or false and Q being true or false. Now, with or, in English, when we use it in spoken English, there's really some ambiguity there. It might be what we call inclusive, it might be what we call exclusive. So consider this statement: do you have math or English at 11 a.m. on Mondays? You're not expected to say, oh, I have math and English at 11 a.m., not a likely answer. So here the or is really an exclusive or. One would exclude the other. You're not going to have both. Are you taking ASL or biology? Well, here the answer could be both, so that's the inclusive or, meaning we could include both answers. That's the English language. Now, in math or logic, when we use our symbol, P or Q, that we mean the inclusive or. So P or Q means either P or Q or both. That could include both. There is a symbol for exclusive or, but we're going to talk about our regular inclusive or. So what are the truth values for P or Q? Well, let's take this case. Tony has a father or a stepfather. When is that going to be true? Well, if she has a father, it's automatically true. If she has a stepfather, it's automatically true. If she has both, she could have a father and a stepfather, then it's still true. So really, it's true unless both of the component statements are false. The only way this statement is not true is if Tony does not have a father and does not have a stepfather. We can now define disjunction, where P or Q is false. Here's our definition here. P or Q is false only if they're both false, and otherwise it's going to be true. We can use our truth table. Here's our truth table. It's only going to be false if they're both false. So this is the case where they're both false. And in every other case it's true. As long as at least one of them is true, then P or Q is true, because either P or Q is true if one of them is true. Again, we listed all our combinations. A correct list could be written in a different order if you, say, switch some of these rows around, but the way I've shown it is the typical way we like to see it. Now we want to define negation. The negation that's not P, or the negation of P, has the opposite truth value of P. And remember, there is this other symbol which can also be used. We have two symbols commonly used for negation. Here's the truth table. We just have P and not P. Well, not P has the opposite truth value, so when P is true, not P is false. When P is false, not P is true. There is an order of operations for these different operators. Negation is done first. Wherever you see negation, you do that right away. So not P and Q means you're going to take not P before you do anything else. That's really the same as putting the not P in parentheses. With the parentheses around the P and Q, that means here you would do the P and Q first. Conjunction and disjunction, these have the same level, so if you see them all in a row, that's actually ambiguous. You need parentheses to show which two you're going to combine first. With logic, we want to translate from English, and so we're going to take these three sentences. This is our P, our Q, and our R, and here's a combined sentence. Tasha is smart, but she's not taking 2 math classes. Here's Tasha is smart, that's going to be our P, but she's not taking the 2 math classes, so do you see we're going to have P and not Q. Here's another one. Tasha cannot take 2 math classes as well as an ASL class. It might have to do with scheduling. She just can't get 2 math classes and an ASL class in her schedule. So what does that mean in terms of our P, Q, and R? Well, she can't take her 2 math classes. She can't do that. She can't take an ASL class. So that's not the quantity Q and R. Now we can take more complicated expressions and we can evaluate them using a truth table.